Now, we look at these two equations here, right? Let's take mu. The equation for mu is, as we discussed last time, is this one, equation number 33. So which tells you you can take mu bar, which means the predicted position, right, mean, and add to that this quantity, which is a gain or Kalman gain times ZT minus C mu T bar. All right. So what is Z? Z is the measurement. C mu bar is actually coming from your sensor vehicle model, mu T bar, right? The previous predicted position times this output matrix C. This is the difference between what the sensor says and what your model predicts. All right. And you multiply the difference, which is called the innovation, with the Kalman gain. So every step you do that, and you can see equation 34 is much more compact. It clearly explains how you combine these two things together. One is what the sensor tells where you are, and what your dynamic model predicts where you are. All right. So I think I discussed with you last time these two cases when Kalman gain is 0 or 1. It varies between 0 and 1, right? So when Kalman gain is 0, for example, so you decide, okay, mu t, which is my present position, the mean is equal to the predicted position. Prediction comes from the vehicle model. So we do not consider the sensor. Right? This Kalman gain is very much like the sensor. So if the sensor is poor, it's 0. If the sensor is very accurate, you don't need a vehicle model. Okay, you don't need a vehicle model. You just rely on the sensor. So that is when k equals 1. So remember that Kalman gain is pretty much sensor representation, how good the sensor is. If it is a bad sensor, Kalman gain is 0. If it is a very good sensor, Kalman gain is 1. For most of the cases, it is between 0 and 1. Now, the rest of this page is basically reformulating these quantities. For example, take the Kalman gain, and we know that Kalman gain is this. So what is that? On numerator, you have sigma square C, right? So that is coming from the vehicle model, right? Sigma bar here, right? In fact, sigma bar square, the predicted covariance, over sigma q square, that is coming from the sensor covariance. You know, vehicle model has an error. For example, if you take the two-wheel mobile robot, when the wheels turn, robot moves. So there's of course an error here, right? If you cannot precisely say where the robot is by just looking at the wheel motion, right? If you turn the wheels 100 times and you expect it to be at some point when you measure it, it's not there. So there's an error. So this is the modeling error, dynamic error in the vehicle model itself. So that is pretty much the case here in the numerator. The denominator is the sensor. Sensor has some noise, and the variance of that is sigma q square. Okay, now you can substitute for this equation from previous equation because you saw that sigma bar square, right, in the previous slides over here, right? So you got that one, right? So if you bring it over here, you can write it like this. Okay. And then with a simple manipulation of this denominator, rather, you multiply all of the terms within the bracket with sigma q square, right? And also multiply numerator and denominator both with sigma bar t square, you get to this equation. All right. So remember, what is sigma bar? Sometimes you might lose this meaning. Sigma bar is the predicted covariance, okay, or predicted variance. So that is the variance of your prediction, right? You describe your position with the mean and variance, right? So this is the variance, prediction variance. But with the measurement, you correct it, and once you correct it, there's no bar, right? The bar vanishes when you correct it. Right. Then this will bring you to equation 35, which is C sigma bar square over sigma bar square plus sigma q square at time t. So every time step you have to calculate this one. All right. And it also shows you the same thing when sigma q increases, when you have a lot of noise in the sensor, k drops. Okay. And if you further say c equals 1, right, in one-dimensional case, for example, kt is equal to this one. Again, it's pretty obvious if you look at these sigmas, how they are connected together, right? Sigma bar and sigma q. Sigma bar is the prediction covariance, and sigma q is the measurement covariance. All right. We also found earlier that after correction, the position variance is given by this equation. Okay, now there you can see on the left hand side, there's no bar. This is after correction, right? So you can manipulate that equation into this format, right? And after that, you can see right over here in the second term, inside the bracket, you can see the Kalman gain, don't you? Right? So you can see C sigma bar square over C square sigma bar square plus sigma Q square. Right? This is actually the Kalman gain, right? Over here. You can see the same expression inside the bracket here with one additional C, So therefore, you can write that this equation 36, which is in a much more concise format. This is the final or corrected variance of the position, which is equal to 1 minus Kalman gain times C whole thing multiplied by sigma bar square, the predicted variance. Now, if I show this in a diagram so that you can understand clearly, it's like this. At t minus 1, you have some distribution. Now, we describe the position of the robot using a probability distribution function, okay? So now it is at xt minus 1. So here x is actually mu, right? When I say x, it's basically mu. They are same. So at some point and with some distribution. And the variance is sigma t minus 1. You can see it over here, sigma t minus 1, all right? And this is the mean and variance. So now what you do is you use the vehicle model and calculate a new probability density function. So when I say new probability density function, you need to calculate two things, okay? The one is the mean, the other one is the variance, mean and variance. So you go from one mean and variance to another mean and variance. That's what we say, okay, you are going from one probability density function to another probability density function. And on the right, you can see the new probability density function as sigma bar t. Can you see sigma bar t, which is a bit broader? This is what we expect when you extrapolate using your vehicle model. All the errors in the vehicle dynamics come into the new probability density function, making it a little broader. You can see the little broader thing. And what you do after that is you use the measurement and correct the probability density function. So you make another distribution function where variance is narrower. So that is sigma t there. Can you see that? So at the same point, you have two probability density functions, right? They're having two different means, two different variances. All right. The bar that you see here is entirely using the prediction model, vehicle model, and then the other sigma, the other distribution function without the bar is after correcting using the sensor measurement. Okay. So in summary, all of the equations are listed over here, right? Three equations: Kalman gain and mu t. Mu t is the new position, mean position, and sigma t is the new standard deviation. And if you look at these equations very carefully, you can see it's very efficient recursive process, right? You don't have to go far back. You only need to look at the previous step, and then you can calculate the new step. And you also need to know sigma q. Sigma q is the sensor covariance. So you need to look at the data sheet of the sensor manufacturer, right? Sensor data sheet, and somewhere you can find out sigma q. If you don't have sigma q, you need to do an experiment, right? Measure the distance to a known object or maybe many objects, and then get the reading and figure out the variance, because you know how to calculate the variance. Okay, you have to find it out yourself. And also when you look at the sigma, which is coming from um, uh, primarily vehicle, you need to have a good vehicle model, dynamic model, and there you can find out the errors in the wheels and all that, how to calculate sigma initially. So with that, you can use these equations. All right, now page 16 here tells you the process overall, okay, without going into a lot of nitty-gritty equations, right? If you look at what's on the left-hand side, it is mu and sigma. So it's a distribution, all right? Mu t minus 1, sigma t minus 1. Then what you do is that you start moving, right? So which means when you start moving, sigma r comes into the picture. Sigma r means vehicle errors, right? Motion errors. So using that, you calculate another probability distribution function. So that is mu t bar and sigma t bar. Can you see that? Over here, the robot has moved from t minus 1 to t. And now it has all these errors in it, right? So the new mean is u bar t. New variance is sigma bar t, right? T is the timestamp. Now what you do, you bring the measurement. There you can see, Z is the measurement. You read some measurements, right? And also, you know what the sensor is, sigma q. You consider these two together and calculate Kalman gain, right? K. So with the Kalman gain, you create another distribution function at the same time, t, that is mu and sigma. This time there's no bar. Bar vanishes, okay? So this is the process. So from this point onwards, you can go to t plus 1 and so on. So this is how it happens. And in the first part of the process, which is coming from t-1 to t using vehicle dynamics, you use these two equations, don't you? What is that? Mu t, mu bar t, right? You know that is equal to a times mu t minus 1 plus ut minus 1. This is the state space model basically, right? For a single dimension, you can say A is a scalar. So it's a one-dimensional thing. And what about sigma, standard deviation? Well, it is the square error basically. So therefore, it has to be A square sigma square t minus 1 plus sigma square r. That is the vehicle error covariance. Vehicles, there are some imperfections, in wheels and all that. So that is this sigma r. Again, if you do not know it, let's say if you build your robot using motors, wheels, etc., there's no data sheet to look at, right? To figure out what is the motion error variance, right? Because it's your thing, you build, and there are a lot of components in it. So what you want to do is you drive it, right? Very much the same way you did with the sensor. You drive for some revolutions in the wheels and figure out the distance and find out what is the error, right? Then immediately you know what is sigma r. All right. Then once you got to t using the prediction, you use the sensor measurement and you calculate Kalman gain. Okay, Kalman gain can be calculated using this equation. And with the Kalman gain and the sensor measurement, you can actually calculate your new mean and variance using these two equations. Now here in these equations, you don't see the state variables, x, but you can see x is replaced with mu here, right? Because we are not talking about exact position, we are talking about probability distribution. So instead of x, we use mu and sigma, standard deviation. Is the process clear to everybody? And the equations. If you have the overall understanding and you know why it is happening like that, how the probability distribution function gets narrower with the measurement and all that, I think you have covered almost everything we have discussed so far. Right? And a little summary up to that point is that you have to assign probabilities for position, probability distribution, right? And you need to do the convolution, which is basically multiplying the probability distribution functions, right? And adding them together using Bayes filter. This is basically probability theory. And a discrete version, you can use histogram, but if you use the continuous format, you can use the continuous PDF like normal distribution. Okay, I think we have covered everything. I'm trying to summarize what we have discussed so far. And then you use the Kalman filter, calculate the gain using the vehicle prediction model and also the sensor model, right, together. And you can update your position. So when you do that, you can improve your estimation. And this is just an illustration. Robot starts from here, it moves down here, right? And this is the actual path. If you get a video camera or overhead drone footage of where the robot is moving, you know exactly where it is moving. That is the ground truth. And then you have here feature-based, similarity transform-based localization. Somewhere here, this jagged line over here. And then you have the Kalman filter one, which is a bit smoother, right? But still, it has some errors. So this is what we expect to see with the Kalman filter. Now today, I want to discuss with you two-dimensional Kalman filter. because some of the graphics I have shown you are not actually very correct. Why? The graphics is actually in 2 dimension, but we have not discussed 2 dimension yet, right? It's 1 dimension. Um, in robot localization, it at least 2 dimension, x, y, latitude, longitude, and all that, right? So it makes a lot of sense to study at least 2 dimensional Kalman filter. Uh, let's look at the probability section first, right? So this is the 1 dimensional probability distribution function, right? Nothing new to you. You have seen it at least few times. Mean and standard deviation, the variance, 68% probability around the mean, right? Plus and minus 1 sigma. So this is 1 sigma portion of it. You have 68% probability that the robot is there within that region, okay? So the total distribution, right, of this function e to the minus half x minus mu over sigma square is actually square root 2 pi sigma. But probability is a normalized thing. Total probability has to be 1. So therefore, you divide the probability distribution function by that normalized value, the total probability, so that when you integrate the new one, it adds to 1, just 1, okay? These are few calculations at specific points. P mu, what is the height? It's 0.04. This top one is 0.04. Sorry, 0.4, right? And if you go down to 1 sigma point, the probability distribution function value is 0.25. It's not the probability, right? It's the value of the probability distribution function at that point. Probability is the area under the curve from this point to that point. Okay, right. Now, let's bring in 2 dimension here. Now you can see x-axis and y-axis, right? 2 axes. And you can mark the mean x, mean y, and standard deviation for x, standard deviation for y, right? Can you see it over here? Right. So this is the 1 sigma point on x-axis, the 2 points. And on the y-axis also plus mu and minus mu, 2 points. And it becomes like an ellipse, all right? Becomes an ellipse. So this is the 1 sigma error ellipse, right? So now your probability that you find the robot within this area, right, is 68%. Again, let's say the submarine that went missing, right? You want to find where the location is. Now you, after doing this calculation, you say, this is x, this is y, and this is the standard deviation. So then everybody knows, right? This is the spot, and this is the area around it, where you have 68% probability of finding the drowned, submerged submarine. Okay, so like that. In mathematics, what happens is that when you have 2 or many probability distribution functions, right, in the same system, you multiply them together like this, right? You can see it over here. 2 PDFs. Their normalizing factors multiply upfront 1 over 2 pi sigma x sigma y and e to the minus half x minus mu x over sigma x square times e to the minus half y minus mu y over sigma y, all things square. So it is yet another probability distribution function. Now it is in 2 dimensions. So when you simplify it, it becomes like this, e to the minus half, you add the 2 exponents, all right? Now, you can bring vectors and matrices here, right, to reformat the exponent into this format. This is just the exponent. You can write it this way. And it's clear to you, right? you have two quantities now, right? X minus mu x, y minus mu y. So you combine them together as a vector and put it up front as a row and at the end as a vector. And in the middle, you get all these coefficients, 1 over sigma x square, 1 over sigma y square, and put it as this matrix here. Now, if you multiply these three matrices, you get the same exponent up there in the previous line. Okay, right. Now you figure out the two means, I mean, one vector, right? X minus mu x, x minus mu y. So you can actually separate them like this. You have x vector now, which is xy, and mu vector, which is mu x and mu y, right? So any dimension, this is valid. And in the middle, you have 1 over sigma x square, 1 over sigma y square in the main diagonal, and all the other diagonals, off diagonal elements, 0. So this middle matrix is related to this matrix here in equation 39, where you have the same dimension, 2 by 2, but in the main diagonal, you have sigma x square, sigma y square, not 1 over, right? So equation 39 is what we know as the covariance matrix. When you have more than one signal, x, y, z like that, there are variances, sigma x, sigma y, sigma z like that, squares of them in the main diagonal. This is the standard covariance matrix. Okay. In the off diagonal elements, you can have x and y, x and z, y and z like that, right? But in this case they're all zeros. This is the covariance matrix. Now, what you have in your system is actually not the covariance matrix, but 1 over the covariance matrix, right? So that is the inverse of the covariance matrix. Inverse covariance matrix. Right. So with that, you can write equation number 40, right? With 1 over 2 pi sigma square sigma x and sigma y as the normalizing factor times e to the minus half x minus mu transpose to make the column vector to a row vector, and then inverse covariance matrix sigma minus 1 followed by x minus mu. So when I say x, it's not the scalar x now, it's the vector x. All right. Fine. Now, when the variables x and y are correlated, now when you say when x changes, y also changes. A normal two-wheel vehicle or four-wheel vehicle, this is the case, right? You cannot simply control only x, right? When you try to control x, y also changes. Look at a quadrotor, flying vehicles. A lot of vehicles are like that. You don't have complete x and y independence, right? There are special mobile platforms for that. So let's say a typical mobile platform, it's like this, like this. Now, the main diagonal is sigma x, sigma y squares, but the off diagonals are like sigma x, sigma y combination products. All right, it becomes like that. So how do we deal with that situation when the variables are correlated? Okay. Well, a matrix like this, all right, this is a symmetric matrix, you can see. Sigma x, sigma y, sigma x, sigma y of diagonal elements are equal. This matrix can be written in this format. In this format. So what is that format? We convert the matrix into a diagonal matrix lambda 1, lambda 2 in the main diagonal, and all the off diagonal elements 0, right? And we put another vector in front of that, and after that, Vt transpose and V. So this combination, lambda and V, right, you have to select properly so that when you work it out, you eventually get the same covariance matrix here. Okay. You have to find out what are the values for lambda 1, lambda 2, and what are the values for what is V vector. All right. And this is what is called the eigenvalue decomposition. You may have heard of it. The lambdas are the eigenvalues of the matrix sigma, and V are the eigenvectors for each of these eigenvalues. So each eigenvalue has eigenvector. So lambda 1 has V1, lambda 2 has V2. Okay. So this V can be written like this: V1, V2 is eigenvectors, two eigenvectors, and here also V1, V2, and this is the main diagonal. Lambda 1, this is lambda 2. Okay, sorry about that. Now, let me bring this example so that you can understand what it is. Now, think about a spur gear like this. You know spur gears, right? One wheel connected with another wheel of a different dimension. When you turn one wheel, the other one also turns. They are coupled. So obviously, you know, these are correlated. These two wheels are related. They are not independent. There's some sort of connection. They are related to each other. So we are going to find out the error covariance of the gear wheel. Okay. Now, if I say the first wheel is twice as big as the second wheel, what I have is actually 1 to 2 gear, right? 1 to 2 spur gear. So the motion of the first gear is X, motion of the second gear is Y. X and Y are angles here, all right? And I also know that the motion is normally distributed. So when I say motion is normally distributed, what I mean is that if I want to turn it to some position, right, I always get to that position plus or minus an error. That's what I say. My most probable location is exactly what I want it to be, but there's always a stochastic error, right, which is plus or minus something, right? So I assume X and therefore Y both normally distributed with zero mean, right? Zero mean means when I want to turn X to, let's say, one radian, it goes to 1 radian. So mean is 0, but it has some plus or minus little error. If you do this 1,000 times, you will see the mean is 0. Mean is 0 means mean error is 0. Okay. Now, if you want to calculate the covariance, this is the equation for covariance. How do you define covariance? It is the Z minus expected value of Z, right? Remember the covariance table that we calculated earlier? What you measure minus the average and multiply the same thing, right? You get the square. So expected value of the square error, sum of square errors, right? That is the variance. So here we have two variables, X and Y. We use the name covariance, right? So this is the equation to calculate the covariance matrix. Here the Z is the measurement. Now you have two measurements, X and Y. Right? So what is the expected value of X? That is expected value of X. 0. Right? I think you understand that. If I want to turn first wheel to some angle, it actually goes there without any error. So that is why I say expected value of X is 0, which means error, okay, not absolute angle. And what about EZ then? EZ means both X and Y. Expected value of X, expected value of Y. So they're both zeros. They're both zeros, okay? This gear has no mean error in either of these wheels, but they have some errors around that reference point. When you want to turn it to some reference point, it always gets there, X and Y both, right? That's why the 0 is there, but there is a little error around it. Now in this equation on the left-hand side, right, you can calculate the covariance matrix when you multiply Z with Z transpose. So what is Z? Z is X and 2X because they are coupled, Y equals 2X. So you can write Z as X and 2X. And the transpose of that is X and 2X as a row. And when you multiply, you get this one. Okay. And you get X square out of that. Then it becomes 1, 2, 2, 4, right? As your covariance matrix. And then expected value of X square. X square is the error square, right? All of the errors you try this for 1,000 times, million times, you get different errors, square them, add them together, divide by the number of samples, and that is your expected value of the error, right? And for this gear wheel, there's a finite value for that. It's not 0. So that is sigma X square. Okay. You can find out sigma of your device, right, experimentally, okay, and get the square of that, and that is the variance or covariance. And according to this arrangement here, two gear wheels, you get this matrix here. Okay. Now this is your covariance matrix of the gear wheel. So this is how you build a covariance matrix of any system. Right? For a mobile robot, you can write the equation and figure it out. For gear wheel, I have just shown you how to do that. Now, we want to do the eigenvalue decomposition of the covariance matrix here. So for that, what we do is we use this one. The determinant of the matrix A minus lambda I. Lambda is the eigenvalue vector, okay? I is the unit vector. So A is 1, 2, 2, 4 minus lambda times I. Determinant is 0. And you multiply, sorry, you combine the two together, A minus this matrix. You get the determinant of this matrix. And once you calculate the determinant and solve for lambda, you get two values. The two eigenvalues here are 0 and 5. 0 and 5. Now for each eigenvalue, you have to find out the eigenvector. Let's take lambda 1 equals 0. You have to find out the eigenvector for that. And that is, let's call it V1. And it is V11 and V12, the vector. All right. Now, how to find out V1? Well, this is the equation to calculate V1. So it is A minus lambda 1 I whole thing times V1 is equal to 0. So this is the eigenvalue decomposition process. So you substitute for A lambda 1 is 0, and then V1 is what we need to find out. So that is V11, V12, all things is equal to 0. And once you do a little, once you expand this one into two equations, you get V11 plus 2V12 is equal to 0. The other one is 2V11 plus 4V12 is equal to 0. And you will see that these two equations are linearly dependent, which means it's the same equation written twice after multiplying by a certain factor, right? So how the two elements are related to each other is this actually. V11, one of the elements in the vector, is equal to minus 2 times the other element of the vector, right? So you can pick up anything over here for V1, right? Uh, so as long as you can satisfy this relationship. So I would take the small values, right? First, I can take any value, right? If I take V12 as 1, right? V11 is minus 2. So I get the smallest whole numbers, right? I could have taken 100 and 200. That's also fine. 1,000 and 2,000, million and 2 million, right? They're all the same, the vectors, right? Here, what is important is the direction. So let's use the smallest integers to make life easy. So I pick up 1 and minus 2 as my V1. So the first eigenvalue is 0 and the eigenvector is minus 2, 1. Same process. Apply this for lambda 2 and V2 and you can calculate lambda 2 is already known, right? 5 and lambda V2 is actually 1, 2. Now let us draw the eigenvalues and eigenvectors on the diagram. And you can see it over here that V1, right, minus 2 and 1 is like this. You can see it over here, V1, right? But the size of the vector is 0 because the eigenvalue is 0. So you have a direction, but vector size is 0. And on the other hand, you have the second eigen value, that is 5. The direction is 1, 2. It is this direction. Can you see it over here? This one. This is the 1, 2 direction. And the size of the vector is 5. Okay. So it is just a line now. Just a line. Okay. So the error distribution, right? We saw earlier something like this, an ellipse with the two major axes aligned with x and y direction. Now it is oriented like in one direction. You have the major axis, but mine axis is 0, right? So this is a perfectly coupled system. The two wheels are perfectly coupled. So when there's an error in one direction, we have like proportional error in the other direction. Okay, so they're tightly coupled. Small error, small error, big error, big error in the same proportion. The two gear wheels are like that. But if you have some other imperfect coupling, when you rotate one wheel, the other one does not rotate by the same amount, right? Some sort of a backlash and all that, then you will see your 1 sigma ellipse something like this. It is disoriented, but you still have two axes, major and minor axis, non-zero, right? Which means there's some sort of coupling, but they're not perfectly coupled. Okay, right. So the message here is that you need to write down these basic equations and try to find out the eigenvalues and eigenvectors when you have a coupled system to figure out the error covariance matrix. All right, it's very straightforward. Once you find out lambdas and v's, you know how to mathematically describe the coupling and therefore the error covariance matrix. Because for you to apply Kalman filter or extended version of that, you need to develop this error covariance matrix. All right. Now here I summarize again one-dimensional case and n-dimensional case. You can see 1D case, you have the probability distribution function like this, and this is the power density or probability density function. Okay, for n-dimensional case, normally distributed, it's like this. Okay, you can see the similarity. 2 pi sigma to the minus half, right? So here sigma square in one-dimensional case, small sigma square. Now it is big sigma. Inside big sigma, you have small sigma squares, right? All of them. And then the exponential part of that, right? Now we have vectors. X means x, y, z, and so on. Mu means mu x, mu y, mu z, and so on. All of the means of the individual variables. And then epsilon, sigma inverse. That is the inverse error covariance matrix, right? Any questions so far? Let me ask Vanuka.
No, this one's clear. But I have to go
Hmm?
this one.
Is
It's
it
clear,
clear
but
to
I have
you?
to go through.
Yeah. Then Tamira, is that clear to
Yes,
you?
yes, sir. Overall idea is clear, but I have to go through again.
Yeah. So I have spent a lot of time preparing these handwritten notes and a lot of tipex here and there to make it as easy as possible for you to digest all of these things. So read it again and again and again. If you read few times, right, every time you read it, you consolidate your knowledge and memory about these equations, and it will give you huge amount of knowledge how to deal with this uncertainty, how to use the probability to express position of a vehicle, okay, and also how to correct the position using sensors. All right. Let's take a little break here, about 10 minutes, and after that, we'll start the second part. All right, now here you can see side by side one-dimensional localization and n-dimensional localization. All right, you can think about the left-hand side as a robot going along a straight line, one dimension, x direction, okay, and you are trying to predict the position and correct the position. And on the right hand side, this is the, say, two-dimensional case, xy. Robot is moving in not a straight line, right? Any direction, curved path on a xy plane, and you are trying to predict the position and correct the position, right? Now, if you look at the compare the equations, one-dimensional case is pretty simple. You can see the first equation xt, state transition equation, right? This is known to everybody. You see a t xt minus 1. This is the homogeneous part of the state transition. But when you have a control signal ut minus 1, right, you change the position because of the control signal. And also there can be unmodeled dynamics that will add to the position certain quantity, that is the sigma r here, or call it epsilon r here, right? This is any unmodeled dynamics in the process. We write it in equations, but practically there's no way to predict it. All right. So similarly, in the n-dimensional case, we have this equation, right? Very similar. Only difference is now instead of scalars, we have vectors. Sorry, matrices. You can see the state transition matrix here, AT, X, T minus 1. Okay, homogeneous part of the vehicle dynamics. And then BT, UT minus 1. This is the drive matrix, right? In state space, you have studied all of these things. And unmodel, anything unmodel, right? Process noise, we call it noise, but it is actually not a noise. It is anything unmodeled, but actual dynamics of the system, right? The second equation is very similar to the first one. In fact, it's the same equation in one-dimensional case. As you know, mu means the mean position. So it is basically the state variable itself, okay? In probability distributions, right, we don't talk about x, y, right? We talk about mu x, mu y. So in the n-dimensional case, same equation, but with vectors and matrices, all right? What about the predicted covariance? Now, you remember the probability distribution functions I showed you from t minus 1 to t. There are three probability distribution functions, or probability density functions rather, right? One is at t minus 1, the other two at t, right? So one of them is with mu bar and sigma bar, that is a predicted probability distribution function, and the other one is mu and sigma, corrected quantities, all right? So this is the predicted one. So because we are talking about prediction now, right? How to go from t minus 1 to t without sensors. So if you look at the right-hand side, in case of n dimension, right, you have error covariance, that is big sigma, and it is coming from this equation, very similar to what is there in for one-dimensional case. Okay, we have seen all these things, and also look at that one. This is process noise covariance, right? Which is basically this process noise. This is just noise kind of thing. Um, um, is a single quantity or couple of quantities together. But when it comes over here, it is covariance. These are square error, mean of square errors. Okay, right. Then we incorporate the reading. So reading comes from here, right? A set of state variables combination plus you have the sensor noise. And this time this epsilon q is the sensor noise. It's a stochastic signal, a random signal, and there's no way to predict it. But if you calculate square of these errors and add them together and get the mean, you get the standard deviation. That is sigma q, right? That is known. Even though this one is not known, this is known after experiments, right? And on the right-hand side, you have the sensor reading. It's a very similar equation, right? Then you calculate the Kalman gain here, and here Kalman matrix. All right, so gain becomes a single gain in one-dimensional case is now a matrix in n-dimensional case. All right. So look at all these things, very similar both sides, right? And Now you correct your position, you calculate the corrected mean and corrected covariance. Okay, one-dimensional case, and this is the n-dimensional case. All right. Now, I think we want to implement this extended Kalman filter based self-localization of a mobile robot, right? Then only you will be able to understand all these equations and how to get these equations into an actual problem, right? Without that, you're not in a position to implement these equations in an algorithm, right? Okay, so I will take the same example, the two-wheel robot. And you can see the same robot here that we started with 2 weeks back. The robot is moving and taking a little curve to the left, and the radius of curvature, instantaneous radius, is capital R, and it in a small time it turns by an angle of alpha, and the left wheel goes by a length of L, the right wheel goes by a length of simple R, and the length between the wheels is W. And you have these equations. I don't want to explain it again. And the diagram here tells you details about the two positions at t minus 1 and t, right? You can see it over here, position at t minus 1. This is the position at t, all right? And the heading at t minus 1 is theta t minus 1. Heading at t is theta t minus 1 plus alpha, because alpha is the angle it undergoes from t minus 1 to t. It's a bit jagged, but you can see these lengths and all that. If this is theta t minus 1, right, um, and if this is alpha, right, you can find out these angles here. As you can see, 90 minus theta minus 1 plus alpha. This is alpha. And you can write the equations here. So you can see what is xt. Xt is the x coordinate at this point. That is from here to here, right? From here to here. Y is this height, because you measure x and y from with respect to this point over here, right? Now, because this angle is 90 minus theta t minus 1 plus alpha, the radius here is r plus w over 2, right? This height is actually sine of this angle, which becomes cosine because this is 90 minus. Okay. And this total angle is 90 minus theta minus 1. So it becomes r plus w over 2, right? Sine 90 minus theta minus 1, which is cos theta minus 1. So you can see it over here, cos theta minus 1 minus cos theta minus 1 plus alpha. Okay. You got that point? So once you have xt minus 1 here, right? Xt minus 1 here, you add to that this distance from here to here to get the x coordinate over here. This little distance is r plus w over 2 sine theta minus 1 plus alpha minus r plus w over 2 times sine theta minus 1. So you can write these two equations for x and y very easily. So I request that you do this as homework, right? Draw it and write down these three equations. Pretty simple, just mathematics, geometry, and trigonometry, okay? And by the way, this equation, which is number 44, is a very, very important equation. Even though it's a very simple equation, right? The robot at two positions. You find out the heading and the small angle, it turns to the left, right? And you write down these two equations. And also, if you look at the heading, theta t is equal to theta t minus 1 plus alpha. Okay. This is the vehicle model. Now, what are the independent variables here? Is R a variable? Yes, R is a variable because it comes from the left wheel and right wheel positions, right? So, in fact, the controls are L and R here. L and R. How much the left wheel turns, how much the right wheel turns. These are the variables, right? So, capital R depends on L and R. So, therefore, this function is actually it depends on L and R. These are the control variables. So make no mistake, right, that you identify what are the control signals here. It is simple L and simple R. Well, what are the state variables? State variables are, of course, the position, X, Y, and also the heading, that is theta. Okay, not alpha. So you figure out very important thing here. One is you identify the state variables, that is X, Y, theta, and you identify the control variables, that is L and R, two control variables. All right. Now, this equation is nonlinear. This is not a linear equation. So therefore, some of the things we discussed earlier with regard to the Kalman filter, right, is not applicable here. The standard Kalman filter is based on the linear systems. You can't have sines, cosines in your model. If you have sines, cosines, you better linearize the equations and get rid of sines, cosines, squares, etc., all nonlinear terms, and make it a linear model, right? And then you can implement Kalman filter to combine the prediction and the measurement. Here, we don't do that. We want to continue with the nonlinear model. And that's why we're going to change the Kalman filter into the extended Kalman filter. Okay, right. Either you can keep the filter standard Kalman and change the model to linear, or don't change the model to the linear, keep the nonlinear model and change the filter to extended version of it. Right? So equation 44 is extremely important. You got to have this dynamic model, right, built before we get going with anything in localization. Okay. And if the robot is not turning either to the left or to the right, if it is moving straight, well, you can use the same equations here, right? And make sure alpha is 0, and you have this equation. So therefore, there's no problem. You have a dynamic model which explains the straight motion also, right? Okay, equation 45. Now, if you look at this equation and on the right-hand side, basically, right, you see there are 5 variables, okay, and 3 equations. X, Y, theta, L, R are the variables, and we have 3 equations. And you can separate the 3 equations into state variables and controls separately. And you have 3 equations, and you can differentiate the 3 equations with respect to the state variables or control variables. All right. Once you do that, you generate what is called the Jacobian. All right. When we deal with nonlinear plans, we need the Jacobian to tell us the rate of change of the variables with respect to each and every dependent variable or state variables and control variables, and then estimate the future position. All right. So therefore, uh, we're going to find out this matrix now, equation 46. This is the straight Jacobian. Straight Jacobian. You can see the three rows. These three rows are basically the three equations, and you see the three columns. The three columns are the state variables, x, y, theta. So you get the first equation for x and differentiate it with respect to x, y, and theta. Okay. Then the second equation for y, t, right? And differentiate it with respect to x, y, theta. So like that. Okay. So once you do that, you can step up to what is called the extended Kalman filter, right? This is the linear case on the right hand side, all what we have seen already, and you now change your equations into the extended version of that. So look at the first one. Xt is equal to at xt minus 1 plus bt ut minus 1 plus the noise, predict unmodeled dynamics. I have crossed it over here just to mention you, just to convey you that this is not something we can calculate and put in there. All right. So in most of the simulations, either you generate it randomly or just put it zero, don't consider. But any error because of that will be seen when you get the measurement. When you get the measurement, it tells you exactly where you are, even though you have missed it over here, certain dynamics. All right. So that equation, we cannot write exactly what it is now. So we say just g of xt minus 1 and ut minus 1, some nonlinear function. Okay. And what about the second one? This is the same first equation, but without saying x, y, or whatever, we say mu, mean, because in the probability, we describe the position using the mean position. Okay. So you can see the same correspondence here as well. So we have some function g, the same function that we use to describe x here as well. What about third one? Third one is the covariance of the prediction, right? Because probability has two terms, mean and covariance. So this is that. You can see the right hand side, familiar equation with this RT, right? Coming from the prediction model, the error model. You saw the gear wheel system, how to get the error covariance and all these things, right? Now, in the extended version, it'll look like this. Now you have to find out what this RT is, right? Based on your system. And also this big sigma in the middle, right? T minus 1 is also something you need to calculate. And Js is actually the Jacobian over here, 46. Once you have the vehicle model, you can calculate the Jacobian matrix, Js, from that. Now, so much of this depends on this G function, nonlinear function G, right? So therefore, we better write it down again here, right? So this is vehicle dynamics, nonlinear dynamics, function G, let's call it G. So it has X, Y, Z on the left-hand side, and the right-hand side is actually the increment of that from X, Y, theta, present value, how to get to the next value. Okay. Now we differentiate it with respect to X, Y, and theta. X, Y, theta, X, Y, theta. These three equations. And you can see the first column becomes 1, 0, 0. Second column becomes 0, 1, 0. Please do this at home, right? And make sure they're all correct. And the third one, partial of Q1, or sorry, G1 with respect to theta. You differentiate this with respect to theta, right? And this one with respect to theta, and this one with respect to theta, right? So when you do that, you get these equations. Now, so these terms are pretty all right, zeros and ones. We are happy about it. But these ones are not. So we better check that out. So what about this one? Partial of G1, this one, with respect to theta. So you want to differentiate this with respect to theta, and this one is of course 0, right? With respect to theta. So, so let's rewrite 1,3 term in Js with alpha equals 0. So if you get this one with alpha equals 0, now when the robot is moving straight, we still need to have this Jacobian, all right? But the problem is when alpha is 0, right? When alpha is 0, this becomes cos theta minus cos theta, which is 0. It looks like it's just 0, but it is not the case. As you know, R is equal to L over alpha, which is also equal to R over capital R plus W, right? So when R is equal to L, which is when the robot is moving straight, alpha is 0. So when the alpha is 0, right, this R is infinity. It's not defined. That's the problem. You can't just simply put alpha equals 0 and say all thing is 0. No, it's not the case. Okay, so it's not defined. It's like you need to use what is called the L'Hopital's rule of differentiation and find out the actual value when alpha equals 0. Now here I have elaborated that process to you. You can see this one, R plus W over 2, then cos theta plus alpha minus cos theta, this one, right? And I have expanded it in the second row here, R times this plus W over 2 times the same thing. Now, W is a constant, and when alpha equals 0, this whole thing is 0. That's all right. No problem with that. But the problem is over here. What about this part when alpha is 0? Now, because R is equal to L over alpha, we are actually having this expression. We are actually having this expression, L over alpha, then cos theta plus alpha minus cos theta. Now, when you put alpha 0 here, the numerator is 0, denominator is also 0. So it's a 0 over 0. It's not defined. You can't just say it is 0. So the L'Hopital's the L'Hopital's rule says that when you are in a situation like that, you want to differentiate the numerator and denominator with respect to alpha, and then take the limit alpha goes to 0. Okay, I think you remember this one from first year mathematics, maybe. So once you differentiate the numerator with respect to alpha, you get this one, L times minus sine theta plus alpha. And when you differentiate the denominator with respect to alpha, it's 1. Okay. So therefore, the answer is minus L sine theta. Okay. When alpha equals 0, this is simply minus L sine theta. Similarly, you can find out the second one, a similar expression, right? So let me show you these expressions over here, right? The second row, last term would be just L cos theta. So therefore, when alpha is 0, this is the state Jacobian. All right. When alpha is not equal to 0, this is the state Jacobian. Right. So equation 47, you have got earlier the vehicle dynamic model, and now you have got the state Jacobian. Now, if you do not want to do the analytical Jacobian, you can still go ahead with the numerical Jacobian. All what you need to do is to find out the quantities of the Jacobian, say G1, right, at two instances. This is t plus delta, x plus delta x, and this is just x, right? You change x by a little amount, divide by delta x. This is basically the rate of change, okay? And then you do the same thing for y plus delta y, here just y, and divide by delta y. And this is for theta, like that. All of these rates can be calculated by taking that respective variable and add to it a little quantity, and then evaluate it and get the difference divided by that little quantity, right? And if this little quantity is very, very small, you are closing in, your numerical value would be very close to the analytical value. So that is also a possibility when you want to implement this algorithm computationally. So where do we get this Jacobian into our localization process? Well, it is, you have already seen, it's over here, covariance, error covariance. So that needs Jacobian, state Jacobian, as well as this RT. In fact, this RT, the error coming from the model, right? Error comes because of the controls also, okay? There are two wheels that are driving the robot. The errors in the wheels contribute to the prediction covariance, of course. So that part is inside this RT, okay? Inside the RT. So this is the equation that we use to calculate the covariance of the prediction, the corrected covariance. Okay, so I'm always telling you we are chasing after two quantities. One is the mean, the other one is the variance. I'm telling covariance because I have two variables now, x and y. So we need to execute this highlighted equation, equation 49, which has on the left hand side the state Jacobian, on the right hand side the control Jacobian. So again we use the same vehicle model and now differentiate it with respect to the control variables. All right. So what are the control variables? L and R, left wheel, right wheel. If it is a two-wheel or differentially driven system, so two wheels. If you had a different mobile platform, you have to use those equations and figure out how many controls are there. Okay. Now, when you write the control Jacobian, right, it is JC over here, but it comes in this format with the control covariance right in the middle. Control covariance right in the middle, right? So if you have two-wheel system, the control covariance matrix would be like this: left wheel, right wheel, standard deviation square, right? You figure out what is the standard deviation of the left wheel, what is the standard deviation of the right wheel, okay, separately. Do the testing, turn the left wheel 100 times, calculate the distance, measure the distance, get the error. Always it's like that. Do the same thing for right wheel. Take the right wheel out of the robot, turn it 100 times, calculate the distance, measure the distance, get the error, get the square, and get the average. So then you have sigma L, sigma R, standard deviation, and get the squares, you have the variance, right? So it's a constant. For a given platform, it's a constant. But the thing is, when you put this in the dynamic model, it is moving together, two wheels together. So they are now connected in some way. So that is why you have to put this control Jacobian also together with the wheel covariance. Okay. So the middle part, big sigma superscript C, is the wheel covariance, independent wheels. All right. Now, when you put it in the robot, the error covariance is different. That is why you calculate it this way. All right. So we need to find out control Jacobian J superscript C. And for that, you need the vehicle model and differentiate partially with respect to each and every control variable. Here we have two, L and R. And this is that equation. Equation 50. And it goes on like that. First one is partial G1 with respect to L. So this is G1. And with respect to L, it goes like this. Okay. So a bit of, you have to recall your memory about differentiation partially. And then we have quotients also, right? And if you look at the first one, when you differentiate with respect to L, this goes out. X is independent of L, right? So we don't care that. And W over 2 comes over here. And then this is a product, right? These two brackets you consider as a product, and you take the second one, for example, the sign terms times differentiation of this quotient here, R plus L over R minus L, goes like that, plus the big bracket here, R plus L over R minus L times, you differentiate the sign terms here. Okay, follow it up, and you can get these equations for the partial derivatives. Okay, this would be a very nice experience for you to refresh your skills on partial differentiation and chain rule, differentiation of a product, and differentiation of a quotient, all of these things. And once you assemble, you get your control Jacobian like this. And when the robot is moving straight, alpha equals 0, and you can write down your control Jacobian reduced form when the robot is moving straight. Okay. Right. Now, to tell you a little more about the wheel covariance, right? Remember this one, sigma, big sigma, superscript C, right? Two wheels, so right wheel, left wheel, sigma squares, right? You can define the error of an individual wheel, left wheel or right wheel, like this, right? The error comes because of its individual motion and also coupled motion, wheel slipping and all that. The wheel slips itself, and also when you combine the two wheels together, there's some more slipping, right? So you can say this is alpha 1 L plus alpha 2 L minus R. So left wheel, right wheel, okay? And put some numbers for alpha 1, alpha 2, maybe 10%, 5%, like that for alpha 1 and alpha 2. And then get the square of the error, right? This is the variance of the left wheel and right wheel. Okay. Equation 54. You can practically do this and calculate sigma L square, sigma R square, and it's going to be a constant. So it's a one-time thing. You need it upfront. before you can execute the loop, recursive loop, you need to calculate sigma c, this one. Okay. Now, let's get back to the extended Kalman filter correction step. These are the equations that are relevant to the correction, right? We have already derived it earlier. Let's show it on the side by side. Kalman gain, mean, and the covariance. All right. So in a extended Kalman filter case, right, on the left hand side, this is a standard Kalman filter. The extended Kalman filter, these are the equations. In the linear case, the measurement is a combination of state variables. And this output matrix CT tells you how to combine the state variables. But in nonlinear case, it's a function that we do not know. You have to find out what is this function. The measurement function, right? Soon we are going to find that out. So, but hold on for that. What about the other things? Kalman gain, it becomes like this. When the measurement equation changes, the Kalman gain also changes this way. Very similar to the previous case, but now it has capital H coming up, right? What is capital H? Capital H is the Jacobian of simple simple H. So simple H is the measurement function over here. You need to write down equations for the measurement model and then differentiate it with respect to the measurement variables. Then you get H matrix. That is also a Jacobian, but this time the measurement model. And keep in mind that you don't measure all of the state variables. If you have n number of state variables, when you measure something else. Maybe part of state variables or something else altogether, right? That's all right. When you write down the equations, you write down how they are related, okay? And their dimension wise also different. Don't have to be the same dimension. Then the rest follows the mean, position, and the position variance, right? Big sigma. They all need capital H. So capital H is the Jacobian of the measurement model. Right, now let me show you the measurement model. So this is your robot. This is the position of the robot, XY. And this is the LiDAR sensor at the front. And the LiDAR sensor looks at one of the markers here. You can see XM, YM. This is one of the markers, landmarks. And it measures the distance to the landmark and also the angle alpha from the heading. Okay. So you can write down the laser scanner position XLYL. XLYL is the laser scanner position as the position of the robot XY over here. And you can see the laser scan is a certain distance towards the front of the robot from the center of the robot. And that distance is D. So when the robot's heading is theta, you can calculate the XY coordinates of the laser scanner using equation 56. Okay. This is the position of the laser scanner. And it's a function of the position of the robot itself. Okay. And then it measures the distance to the marker, that is capital L. So you can write capital L in that equation 57. And also the laser scanner calculates the angle to that marker. And the angle here is alpha. Of course, previous alpha and this alpha should be different. So therefore, I think I have to edit this again. I will put a little subscript here, alpha m, to say that this is the angle of the marker. Okay, alpha m. So this is not the previous alpha. Now, these are the measurements, L and alpha. So L and alpha is actually the Z vector. Z is the measurement vector. So L and alpha is the measurement vector. So you can write down the two equations here, right, as H or Z, equation 58. This is your measurement model. There you are. Earlier you had the vehicle model. Now you have the measurement model. Okay, so these equations are pretty straightforward modeling equations. You just need to take a piece of paper, draw your system, identify variables, write down equations. Okay, what you are measuring here, you are measuring capital L, the distance to the marker, and also the bearing of the marker from the heading of the robot. Now you need to get the Jacobian of this one with respect to the state variables. The state variables are x, y, and theta. Entire story, right from the beginning, our state variables are x, y, and theta. Now we have two equations for the measurement, capital L and alpha. You differentiate these two equations partially with respect to state variables, right? That is x, y, and theta. And you can see all these state variable, the partial derivatives rather over here. Can you see that? Partial L over partial x, partial L over partial y, partial L over partial theta. When you do the differentiation, you have to be careful a little bit. When you differentiate with respect to x, right, you need to keep that in mind that x comes inside xl in the equations. These equations don't have x explicitly. They have xm, xl, ym, yl. xm, ym are constants. If you look at this one, is the marker's position. They're constants. Once you identify this is marker number 3 or whatever, you know their exact coordinates. They are constant. The variables are xl, yl, and xl, yl are, they depend on xy. This is how xy comes into the picture indirectly. Inside xl, there is x. Inside yl, there is y over here, right? xl and yl. So now when you differentiate with respect to x, right, you can do that this way. First, differentiate with respect to xl, and then use the chain rule, partial xl over partial x, which is 1. So that is why this 1 is over here. In fact, minus 1 because it is minus xl. Okay. All right. And also, you have to differentiate this one also, right? Arctan, this quantity minus theta. So you need to know what is the differentiation of an arctangent. You can see it over here. Arctan x with respect to x is 1 over 1 plus x square. Use that one. And also, as I said earlier, you can first differentiate with respect to xl and then differentiate xl with respect to theta, right? So when you do that, you can get all of the partial derivatives. And now a lot of these partial derivatives, they come with xm minus xl and ym minus yl, right? So this is the x gap and y gap, okay, x distance and y distance. And also you can see the square root coming up over here, square root of xm minus xl square plus ym minus yl square. This is basically the measurement length, okay, which is capital L. So you can put it like this over here. All right. So with all of these things, you can write down the partial derivatives like this. This is the partial derivatives of L with respect to x, y, theta. And similarly for alpha, which is arctangent of this expression, when you differentiate with respect to again x, y, and alpha, you get these three terms. And when you combine the two together, you get matrix H. This is the measurement Jacobian, right, with respect to the position, state variables of the system x, y, and theta. Equation 59. Is that clear up to now, Banuka?
Yes, it's clear for me.
All right. Chamira,
Okay, sir.
you're following, right? Yeah. But I'm sure not everything goes right into your brains, right? What I expect today is that you figure out the path so that you can go through this lecture material. Of course, I will revise and upload a new document. Then with the slight modifications, you need to read the document, not once, maybe 3, 4 times, right? And also do some of these derivations, right? It will help you actually to develop your analytical skills. More than that, to understand what you are doing using mathematics, right? What is it that you are doing actually in the physical world, right? What is the real physical meaning of these mathematical equations? So you got to understand that one, right? Otherwise, you're doing some mathematical process but not knowing what it really is, right? That's not good. No? Okay. Now we have come to probably the last slide. With these nonlinear equations and also with their partial derivatives, we can implement the extended Kalman filter, and we can improve the accuracy. Now here is just an illustration. Actual path of the robot in red color and estimated path in black, very close to each other. Okay. Now I want to show you the entire process as an algorithm now, right? We have spent a lot of time on each and every subsection earlier to derive some of these equations. So therefore, maybe now your work table is pretty messy, a lot of equations on your table. Now I want you to group them together, bring some order into these equations, right? And arrange them in a proper manner. So this is how you implement extended Kalman filter for localization. Number one, you need epsilon 0. What is that? Initial covariance. Where is my robot? If you look at the initial distribution, right, it has a mean, probably you can say mean 0. What is the standard deviation? You can put some random number if you want initially, because when you don't have anything, All right. Number two, so not number two, under number one, you need x0. What is your present position? X0, right? You need to put that also. This is where you start the robot motion. U0, what is my control signal? Initial control signal, right? You have to put that there. If you don't have any control signal, if you put 0, it's not moving actually. Without any control signal, it's not moving, right? So therefore, you better put some control signal up front. Then theta 0, what is your initial heading? Whether you are going north, south, east, west, where it is, right? The theta 0 is important. And Q. So what is Q? Q is coming from equation 55. So go back and figure that out. 55. I have put the numbers here. 55. This is the epsilon superscript C. This is the wheel motion covariance. The two wheels, left and right wheels. So you do a little experiment, individual wheels, do the testing and figure that out. What is sigma L? What is sigma R? Okay. And put it over here. Right, you have got that as well. Now you need from this one, you can figure out sigma C using equation 54. It's the same thing. I can pedal back and show it to you. This one's right. So how you actually do this experiment to calculate epsilon C, sorry, sigma C. Okay. This is the first major thing you need to do. All right. Figure out your wheel covariances, errors in the wheels. Okay. Then use the vehicle model. You have to write down the equations for the vehicle model. For two-wheel differentially driven platform, we have already derived the equations, right? That is equation number 44. Remember the three equations, x, y, theta, from t minus 1 to t, and then do the different partial differentiations with respect to the state variables and with respect to the control variables, and find out Js and Jc. Okay, state Jacobian, control Jacobian. So with that, you can actually so what I have written here is to hint you that this is nothing but state transition equation, right? You're familiar with state variable x and how it goes from t minus 1 to t. This is pretty much the same thing, but this time we are replacing x with mu because we are entirely we are describing the position as a probability distribution function. That's why. And then you go to so once you calculate your using equation 47 and 41, 51, the Jacobians, you can actually do the prediction process using 44 and 49, these two equations. Okay, mu bar t and sigma bar t, right? Using the vehicle dynamic model and also the Jacobians, you can calculate the predicted position of the robot and predicted covariance. That is the predicted probability distribution function, the second distribution function. All right. Then what you do is you try to correct your probability distribution function using the measurements. For that, what you do is you calculate the distance to a marker and also the angle to a marker using your sensor, right? Well, you can do the same thing using the sensor here. Use the sensor to calculate ln alpha, that's fine. But before that, you can calculate actually using equation 57 ln alpha. So shall we go back to 57. There you are. Oh, here. This one, ln alpha, right? So you know your x and y, your present mean mu bar, right? Mu bar means x and y basically, and also theta, right? You put those values over here for um, x and y and for theta, right? For this equation, you can put your present mu, mean value, that is x, y, and theta, and calculate xl, yl, right? So once you have xl, yl, you put it over here to 57 and calculate ln alpha. So this is the prediction without any measurements, right? In fact, you need equation 56 also here. I have to add that to this algorithm. 56, 56 and 57 together over here, right? You calculate your ln alpha. So this is what you expect the measurement, the sensor to tell you, right? This is the distance to the marker. This is the angle to the marker. But the sensor tells something else. When you read the sensor, it tells you something else. The length or distance is different, angle is also different. There's a difference between what the model says, what the sensor says. And using equation 55, you can calculate the Kalman gain, and then using measurement, ZT, and also calculate the Jacobian of the measurement model using equation 59, and 59 is over here, right? All of these things are available. Then you can actually calculate mu t, correct mu t, and correct the error covariance. So once you calculate mu and big sigma here, right, you have yet another probability distribution function. This is the third and last probability distribution function in one step, t minus 1 to t. So once you do that, you start over again with number 2, step 2 here, right? Using the new mu, right? You calculate your Jacobians, right? Starting from equation 44 and do the process again. So it goes on and on and on. So this is an extended Kalman filter version of the self-localization of a robot. And eventually, it gets you this result. Much more accurate result than any other technique. The previous technique we discussed with the similarity transforms using multiple markers, all right? And if you compare the two things, there are a few things that I want to mention. The similarity transform case, there are 4 parameters to be optimized. Therefore, you need at least 2 markers, preferably more markers to maintain your accuracy. But here, just 1 marker is enough to estimate your position. Okay, you don't need many markers. If you have many markers, that's also all right. But even with a single marker, it will do the job. And this is computationally much more efficient than any other algorithm, so that you can put it on a real-time embedded system. That's how the robot works. As you saw in the video, it reads all of these LiDAR sensors, right, and then navigate self from point A to point B. All right. So that's about it for self-localization. We have time for a few questions.